Let's now talk about how embedded systems are designed. This slide shows the overall design flow for embedded systems. We start with system requirements that are given in layman's term. From these requirements, specifications are derived, which are the technical details that an engineer or a designer can understand. Given these specifications, the next step is to design an architecture that tells which are the different components that will be needed and how these components should be connected together. Once we know what are the components required, we need to design those components. So some of the components can be picked from standard libraries, whereas some others might need to be custom designed. And the final step is integration, which means to connect these components together and make the whole design work. This approach of going from requirements down to the integration is called top-down design. However, sometimes when you integrate the system, you realize that it does not meet the requirements we started with. Then we need to go back and check at which of the previous stages we need to make changes to meet those requirements. And this approach of going backwards is known as a bottom-up design. In reality, the embedded system design is a combination of top-up and top-down and bottom-up designs. Also, it's not necessary while going up to just go one step backward. We might need to go from integration directly to architecture, or maybe from components directly to specification, or some other combination. Also, while going down, we do not always go from one stage to the next stage directly. For example, while going from specification to architecture, we might decide this architecture is not good enough to meet those specifications, and either we make the architecture again, or we might need to adjust our specifications. So we do not go down from architecture to components, rather we go back from architecture to specifications to redefine our specifications themselves. Okay, so now let's discuss each of these steps in more detail. Let's start with requirements. So as we know, requirements are just an informal description of the system in layman's language. Now the requirements can be functional or non-functional. The functional requirement tells us what the system is really supposed to do. Let's take an example. A GPS moving map. A functional requirement of a GPS moving map can be that it should display a map of the terrain around user's current position. So in a nutshell, it just tells what the system is supposed to do. Then there are also some non-functional requirements which do not tell you what the system is supposed to do, rather some other requirements from the system. And it could be in terms of cost, size, power, or something else. Again, for our GPS moving map system, the non-functional requirements can be in terms of cost. For example, it shouldn't cost more than 1000 kroners. The non-functional requirements could be in terms of size, that it should fit on the palm of a hand, or it could be in terms of battery life. For example, it should run on two batteries that should last for at least 8 hours. Now the next step is to derive specification, and these are the unambiguous technical description that we need to provide the system designer or the engineer. Let's take a look at what the specifications can be. For our example of GPS moving map, one of the requirements was that it should fit on the palm. But the size of the palm can be ambiguous. When we derive specification, we have to give an unambiguous description. In this case, it could be 2 by 4 inches. Again, the requirements of 8 hour on batteries could translate to that the maximum power consumption could be 100 milliwatt, and so on. From these specifications, we have to design an architecture, and this could be the architecture for our GPS moving map. For example, we have an antenna which tells the current location of the user. Then this user location is given to a search engine that searches the nearby terrain in a database. Once you know the location, once you know the location and the nearby terrain, they are given to the renderer, and the renderer displays the location and the terrain on a display. Also, there might be a user interface for the user to interact with the device. The key challenge at this stage is to decide which of the functionality should go in hardware and which should go in the software. As you see, in theory, all of these components can be designed in hardware, but that might be too much cost, or it might be too much power consuming, too much design complexity. So at this stage, we need to decide which of these components should be in hardware and which one should be in software while meeting the system requirements of cost, performance, and power, and maybe more. The next step is to design the components themselves. There are some standard components that we can use, for example, CPUs, memories, software libraries. And in our example of GPS moving map, a GPS receiver and topographic database are good examples of standard components that can be used in our design. The custom components that are generally required are printed circuit boards and software modules that are not standardized. In our example of GPS moving map, a good example of custom component is the user interface. Finally, the integration, just put all the components together and make the whole system work. The key challenge at this step is to find the bugs and get rid of them. Generally, throughout the design process, some unforeseen bugs creep into the system. So at this step, we need to do some debugging. Though careful component design and architecture design, they all help in the not having the bug in the system at to begin with. But however, all the systems generally require some amount of debugging at integration stage. So now we know what are the different steps involved in an embedded system design. Now let's see what are some of the hardware components that are usually required in the systems. First of all, we require some hardware for doing some processing. It could be CPU. However, if your embedded system is really simple and CPU is just too complex of a device for your system, you might need to design your hardware or your processing elements on your own. All embedded systems require some amount of memory. It could be volatile memory, non-volatile memory. Some systems need less memory, some systems need more memory, but they usually all of those systems require some amount of memory. And finally, there are input-output devices. Since an embedded system needs to interact with the physical world, there has to be some input and output devices in the system. And all of these hardware devices are usually connected to each other via something which is called a bus. Now, once you have this hardware, we need to program it. And it's generally programmed in either assembly or C code. And the reason is because these are really lightweight. They reduce the memory size requirements for the code. Also, the code written in these languages is quite fast compared to other high-level languages, for example, Python or Java, etc. So C and assembly are usually the common choices for embedded system programming. So if you have your code written in C, it needs to be compiled down to the assembly language, and the assembly code also needs to be translated down to the machine code, which is done by assembler. Also, while the code is being compiled or translated to machine code, it's a good idea to optimize this code further. And finally, an embedded system may not have an operating system based on the complexity of the embedded system. And so we should know what are the features operating system provides that can be used. So in a nutshell, this slide shows what are the different hardware components and software components in embedded system design. This slide also shows the learning objectives of this course. We will talk about embedded system hardwares, in particular CPUs, memory, I/O devices, and buses. And we will talk about software aspect of the embedded system design, for example, programming in C code and programming in assembly code, how the compilers compile the C code, how the assembler translate from assembly code to the machine code, what are the different optimizations can be applied to this code, and what's the role of operating system, what are the features it provides, and finally we will also take a look at few techniques to reduce the power consumption in embedded systems.